Welcome to this gentle exploration of the universe's ultimate destiny. Tonight, we drift into one of the most profound mysteries that physics has revealed to us: the quiet, inevitable journey toward a state of perfect stillness that awaits all of existence. There is something deeply calming, almost paradoxically beautiful, about contemplating the heat death of the universe. This final chapter, written not in catastrophe or explosion, but in the gradual fading of all motion, all energy, all warmth, into an eternal whisper of silence. Picture, if you will, the universe as a vast symphony hall where for billions upon billions of years, the music of creation has been playing. Stars have sung their nuclear songs. Galaxies have waltzed through the cosmic dark, and planets have spun their ancient rhythms around their stellar partners. But like all symphonies, this one too must eventually fade into silence, not abruptly, not violently, but with a gradual diminuendo that stretches across timescales so vast that they challenge the very limits of human comprehension. The heat death of the universe is perhaps the most peaceful apocalypse we could imagine. There are no explosions here, no cosmic collisions or dramatic collapses. Instead, it is a slow dance toward equilibrium, a gentle settling of all things into their final resting places, like watching snow fall on a winter's night, covering the world in a blanket of quiet uniformity. The universe, too, will eventually settle into a state where every corner, every region, every particle exists at the same temperature, a temperature barely above absolute zero. In our daily lives, we experience hints of this cosmic principle. Think of how a cup of hot tea left on your nightstand gradually cools to match the temperature of your room. The steam that once rose in delicate spirals dissipates. The warmth that comforted your hands fades away, and eventually, the tea becomes indistinguishable in temperature from the air around it. This simple, everyday phenomenon is a microscopic preview of the universe's grand finale. There is something profoundly humbling about recognizing that everything we see, every star that twinkles in the night sky, every galaxy spinning in the cosmic deep, even the warmth of our own bodies, is part of a temporary arrangement, a brief flowering of complexity and energy in a universe that is inexorably moving toward stillness. Yet this knowledge need not fill us with dread. Instead, it can inspire a deeper appreciation for the present moment, for the remarkable fact that we exist in an epoch where stars still shine, where planets still orbit, where life still flourishes. As you lie in bed tonight, feeling the gentle pull of sleep, you are in a way rehearsing the universe's own journey. Your breathing slows, your thoughts quiet, your body relaxes into stillness. This nightly surrender to rest mirrors, in miniature, the cosmic surrender to entropy that governs all things. And just as there is peace in sleep, perhaps there is a strange peace too in knowing that the universe itself will one day rest in perfect, eternal quietude. In this contemplation of endings, we find not fear, but a curious comfort, the recognition that even the cosmos itself knows how to let go, how to release its energy, how to finally, after eons of brilliant activity, simply rest in the quiet depths of physical law. There exists a principle so fundamental, so inescapable, that it governs everything from the melting of ice cubes to the fate of galaxies. This is entropy, the universe's hidden bookkeeper, always tallying, always increasing, never allowing the cosmic accounts to run backward. Tonight, we explore this invisible arrow that points unwaveringly toward the future, this strange quantity that physicists have come to recognize as the very heartbeat of time itself. Entropy is, at its heart, a measure of disorder, though this word barely captures the poetry of what it truly represents. Imagine a child's room, meticulously organized by a patient parent. Toys in bins, books on shelves, clothes folded in drawers. Left to the natural course of play and daily life, this order inevitably gives way to chaos. Toys scatter across the floor. Books tumble from their perches. Clothes form small mountains on chairs and beds. This transition from order to disorder is not merely a human phenomenon. It is a fundamental tendency woven into the fabric of reality itself. The second law of thermodynamics, which governs entropy, speaks with a voice of absolute authority. In any isolated system, entropy must increase, or at best, remain constant. It can never spontaneously decrease. This law is unlike any other in physics. While other laws tell us what can happen, the second law tells us what must happen. It provides direction to the universe, creating an arrow of time that distinguishes past from future, memory from anticipation, youth from age. Consider the delicate dance of molecules in a perfume bottle. When you remove the stopper, the fragrant molecules, once confined to their glass prison, begin their journey outward. They spread through the room, mixing with the air, creating invisible currents of scent that eventually reach every corner. Never, in all the history of the universe, have these molecules spontaneously gathered themselves back into the bottle. This is not because it's physically impossible. The laws of motion would allow it, but because it is statistically so improbable that it might as well be impossible. This is the tyranny of entropy, gentle but absolute. Yet entropy is not merely about disorder in the conventional sense. It is more accurately about the number of ways a system can arrange itself. A sandcastle on the beach represents low entropy. There are relatively few ways to arrange sand grains to create that specific castle, but the wind and waves, in their ceaseless motion, will transform that castle into a scattered pile of sand, high entropy, because there are countless ways to arrange sand grains in a formless heap. The universe always moves toward configurations that can be achieved in more ways, simply because these arrangements are overwhelmingly more probable. There is something almost musical about how entropy orchestrates the cosmic symphony. Every chemical reaction, every biological process, every stellar fusion event pays tribute to this principle. When a star fuses hydrogen into helium, it doesn't just create light and heat, it increases the universe's total entropy. When your body metabolizes food, transforming organized molecules into energy and waste, entropy increases. Even the act of thinking, the firing of neurons in your brain as you contemplate these words, contributes its small offering to the universe's ever-growing entropy. This relentless increase of entropy is what creates the arrow of time we experience. It's why we remember the past, but not the future. Why we age, but never grow younger. Why broken eggs don't spontaneously reassemble themselves. Time itself, in a very real sense, is simply the direction in which entropy increases. Without entropy, there would be no difference between forward and backward, no distinction between cause and effect, no story to tell. The universe would be frozen in a crystalline perfection of reversibility, beautiful perhaps, but lifeless and static. It is entropy that gives the cosmos its narrative, its direction, its purpose, even if that purpose is ultimately to achieve a state of maximum disorder, of perfect equilibrium, of final rest. There is a profound tranquility in imagining a universe where all temperatures have converged, where every particle, every region of space, every remnant of what once were stars and planets exists in perfect thermal harmony. This is the destiny that awaits our cosmos, not a universe of extremes, but one of ultimate equality, where heat no longer flows because there is nowhere for it to flow to. Tonight, we contemplate this final equilibrium, this cosmic democracy, where every point in space will share the same whisper of warmth, barely distinguishable from absolute zero. Temperature, in its most intimate essence, is simply the average kinetic energy of particles, their restless dance, their ceaseless vibration, their eternal jittering in the dark. When we feel warmth, we are sensing the collective motion of countless atoms and molecules, their microscopic ballet translated into the sensation we call heat. And like all dancers, these particles follow a fundamental rule. Energy flows from regions of vigorous motion to regions of gentle movement, from hot to cold, always seeking balance, always pursuing equilibrium. Picture a lake on a perfectly still morning, its surface mirror smooth, reflecting the sky with such fidelity that the boundary between water and air seems to dissolve. Drop a stone into this tranquil scene, and ripples spread outward in perfect circles, carrying energy across the water's surface. But watch long enough, and those ripples fade, the energy dissipates, and the lake returns to its glassy calm. This is equilibrium, not the absence of particles or energy, but their perfect distribution, their democratic sharing of available states. The universe, in its current epoch, is magnificently far from equilibrium. Stars blaze at millions of degrees, while the cosmic void hovers just barely above absolute zero. This tremendous temperature gradient is what makes everything possible. It drives the winds on planets, powers the chemistry of life, fuels the nuclear furnaces of stars. Heat flowing from hot to cold is the engine of all change, all complexity, all stories in the cosmos. But like our ripples on the lake, these temperature differences are temporary perturbations in a system inexorably seeking balance. The mathematics of this cosmic cooling are both beautiful and melancholic. As the universe expands, space itself stretches, and with it, the wavelengths of all radiation grow longer, their energy diminishing like notes from a piano fading into silence. What began as the fierce gamma rays of the Big Bang have stretched into the microwave background, radiation we observe today, a cosmic whisper at merely 2.7 degrees above absolute zero. And this cooling continues, will always continue until the universe reaches a temperature so close to absolute zero that no meaningful work can be extracted from any temperature difference. This final temperature won't quite be absolute zero. Quantum mechanics forbids such perfect stillness. Instead, the universe will hover at a temperature perhaps 10 Taurus or 30 degrees above absolute zero, though such numbers lose meaning in their incomprehensible smallness. At this temperature, even the vibration of particles becomes a kind of theoretical abstraction. It is a cold beyond any earthly imagining, a stillness more complete than the center of the darkest nebula, a quiet more profound than the space between galaxies. Yet there is something deeply satisfying about this destination. In thermodynamics, equilibrium represents the state of maximum entropy, but also of perfect democracy. No region of space is privileged over any other. No particle has more energy than its neighbor. No gradient exists to drive change or create inequality. It is, in a cosmic sense, the ultimate expression of fairness. A universe where every point, every particle, every quantum of space has achieved the same state. As you feel the warmth of your blanket tonight, recognize that this comfort comes from disequilibrium. Your body at 98.6 degrees Fahrenheit, your room perhaps at 70, your blanket trapping the heat that flows from you to your surroundings. This flow of warmth that comforts you is possible only because the universe is still young, still far from its thermal destiny. We live in the brief epoch where temperature differences still exist, where heat still flows, where the cosmic engine still runs. In billions upon billions of years, when the universe has achieved its perfect equilibrium, such simple pleasures as warmth will be not just rare, but impossible, a memory held only in the quantum fluctuations of an eternally cold cosmos. In the industrial heart of 19th century Europe, among the smoke and steam of the early machine age, a German physicist named Rudolf Clausius was studying the efficiency of steam engines when he stumbled upon a truth that would reveal the ultimate fate of everything that exists. It is both humbling and beautiful that humanity's first glimpse of the universe's ending came not from telescopes pointed at distant stars, but from careful observation of pistons and boilers, from the practical concerns of engineers trying to build better machines. The year was 1850, and Clausius was grappling with a puzzle that had emerged from the work of Sadi Carnot, a French military engineer who had died young but left behind revolutionary ideas about heat engines. Carnot had shown that no engine could be perfectly efficient, that some energy was always lost, dissipated into useless heat. But Clausius saw deeper into this principle. He recognized that this wasn't just a limitation of human engineering, it was a fundamental law of nature, a principle that governed not just steam engines, but stars, planets, and the cosmos itself. Clausius introduced the concept he called entropy. From the Greek word for transformation, he formulated what would become the second law of thermodynamics. The entropy of the universe tends to a maximum. These simple words, published in scientific papers that few outside academia would read, contained within them a prophecy of cosmic proportions. Clausius had discovered that the universe itself was like a vast steam engine gradually running down, dissipating its useful energy into waste heat, moving inexorably toward a state where no more work could be done. The philosophical implications of Clausius's discovery sent ripples through Victorian society. Here was science suggesting that the universe had a direction, a destiny, an ending. The eternal cosmos of Newton, spinning forever in clockwork perfection, was replaced by something more like a candle burning down, a spring unwinding, a song fading into silence. the German physicist Hermann von Helmholtz would soon coin the term Wärmetod, heat death, to describe this ultimate fate, a phrase that captured both the scientific precision and the existential weight of what had been discovered. Consider the elegant irony of this discovery's context. The steam engine, that symbol of human progress and industrial might, revealed through its very limitations the ultimate powerlessness of all efforts against entropy. Every piston stroke, every turn of the wheel, every bit of work extracted from heat was simultaneously a contribution to the universe's overall entropy, hastening, however infinitesimally, the cosmic heat death. The machines that seemed to represent humanity's conquest over nature were actually demonstrating nature's ultimate victory over all organized systems. The initial reactions to Clausius's discovery ranged from denial to despair to a kind of cosmic resignation. Philosophers and theologians grappled with a universe that seemed to have a built-in expiration date. The poet Algernon Charles Swinburne wrote of the goal of all life being death, influenced by these thermodynamic revelations. Scientists themselves were divided. Some, like Lord Kelvin, embraced the implications and began calculating timeline for the heat death, while others searched for loopholes, for ways the universe might regenerate itself. What makes Clausius's discovery particularly poignant is how it emerged from such mundane beginnings. He wasn't searching for cosmic truth. He was trying to understand why some heat engines were more efficient than others. Yet in the mathematics of steam and pressure, he found equations that described the destiny of galaxies. In the hissing of valves and the cooling of boilers, he heard the whisper of the universe's eventual silence. This discovery also marked a profound shift in how we understand physical law. Before Clausius, the laws of physics were reversible. They worked the same forwards and backwards in time. But entropy introduced an arrow, a direction, a cosmic preference for certain states over others. It told us that while the universe's past might have been ordered, its future would be one of increasing disorder. That while we emerged from a cosmos of low entropy, we are heading toward one of maximum entropy. As you drift toward sleep tonight, consider that Clausius's equations are at work in your very body. Your metabolism, your breath, your heartbeat, all are tiny engines converting organized energy into entropy, adding their small contributions to the universe's grand accounting. The warmth you feel is the same phenomenon Clausius studied in those early steam engines. Heat flowing from ordered to disordered states, useful energy becoming useless, the universe taking one more infinitesimal step toward its thermal destiny. In understanding engines, Clausius had understood everything, revealing in the practical concerns of the industrial age the ultimate fate that awaits all industry, all life, all stars, all stories in the cosmos. In the gaslit studies of Victorian Britain, a scientific giant named William Thomson, later ennobled as Lord Kelvin, turned his formidable intellect toward a question that would haunt humanity for generations, not just how the universe would end, but when. There is something almost musical about how Kelvin approached this cosmic puzzle, applying the rigorous mathematics of thermodynamics to the grand stage of existence itself, calculating with patient precision the timeline of our universe's slow fade into darkness. Lord Kelvin was already a legend in his own time, a physicist who had helped lay the first transatlantic telegraph cable, who had developed the absolute temperature scale that bears his name, who had contributed to nearly every branch of physics known to the Victorian age. But perhaps his most profound contribution was his attempt to place numbers on the unthinkable, to calculate the age of the Earth and the Sun, and from there to estimate how long the universe had left before the heat death that Clausius had predicted. Picture Kelvin in his laboratory at the University of Glasgow, surrounded by brass instruments and leather-bound notebooks, applying the same principles that governed steam engines to the sun itself. He imagined our star as a gradually cooling body, radiating away its heat into the cosmic void. Using the best knowledge available in the 1860s, he calculated that the sun could not be more than 100 million years old and had perhaps another 20 to 30 million years of life remaining. These numbers, we now know, were spectacularly wrong, off by factors of hundreds. But the method, the audacity of even attempting such calculations, was revolutionary. What Kelvin didn't know, couldn't have known, was that the sun wasn't simply cooling like a hot poker removed from a fire. Deep in its core, nuclear fusion was converting matter directly into energy, a process that wouldn't be understood for another half-century. This is the beautiful humility of science. Even brilliant minds working with incomplete knowledge contribute stepping stones toward truth. Kelvin's calculations, though incorrect in their specifics, established the principle that the universe's energy resources were finite, that time itself was a limited commodity in the cosmic economy. The debates that Kelvin's work sparked were fierce and fascinating. Geologists, studying the slow accumulation of sediments and the patient erosion of mountains, insisted the Earth must be far older than Kelvin's thermodynamics allowed. Charles Darwin, whose theory of evolution required vast stretches of time for natural selection to work its patient magic, was deeply troubled by Kelvin's calculations. Here was physics seeming to contradict biology and geology, a crisis that would only be resolved with the discovery of radioactivity and nuclear fusion. Yet Kelvin's broader vision of cosmic heat death remained unchallenged. He painted a picture of a universe slowly winding down like a grandfather clock whose weights were approaching the floor. Within a finite period of time past, he wrote, the Earth must have been, and within a finite period of time to come, the Earth must again be unfit for the habitation of man. These words, delivered with the authority of mathematical calculation, introduced humanity to the concept of cosmic mortality on a scientific basis. Lord Kelvin also introduced a profound insight about the nature of time itself in a universe governed by thermodynamics. He recognized that in a state of maximum entropy, when the universe had achieved perfect equilibrium, time would become meaningless without energy gradients to drive change, without hot and cold to create flow, without any possible transitions from one state to another. The very concept of before and after would lose all meaning. Time, Kelvin understood, was not just measured by entropy. In a very real sense, it was created by it. The numbers that modern cosmology provides would have staggered Lord Kelvin. We now know the universe is 13.8 billion years old, that our sun has another 5 billion years of hydrogen fusion ahead of it, that the heat death Kelvin contemplated lies not millions but googles of years in the future. timescales so vast that they challenge not just comprehension, but imagination itself. Yet Kelvin's fundamental insight remains unchanged. The universe is not eternal, energy is not infinite, and entropy will have its ultimate victory. As you drift through these contemplations tonight, consider how Kelvin's work bridges the human and the cosmic. He took the same mathematics that described the cooling of a cup of tea and applied it to stars and galaxies. In doing so, he showed us that we are not separate from the cosmic story, but part of it, subject to the same laws, participants in the same grand thermodynamic drama. The warmth you feel from your blanket, the cooling of your room as night deepens, the gradual slowing of your metabolism as sleep approaches, all of these are tiny echoes of the cosmic cooling that Lord Kelvin first dared to quantify, small notes in the vast symphony of entropy that he was among the first to hear. In the coffee houses of Vienna, where the air was thick with tobacco smoke and animated discussion, a troubled genius named Ludwig Boltzmann was revolutionizing our understanding of entropy, transforming it from a mysterious quantity into something we could visualize, almost touch, the statistical behavior of countless dancing particles. There is something profoundly beautiful about Boltzmann's vision, for he showed us that the inexorable increase of entropy wasn't commanded by some cosmic decree, but emerged naturally, inevitably, from the random motions of atoms following simple laws of probability. Boltzmann lived in an era when the very existence of atoms was still debated. Many distinguished physicists considered atoms to be merely useful, mathematical fictions, not real physical entities. Yet Boltzmann built his entire understanding of thermodynamics on the assumption that matter consisted of discrete particles in constant, random motion. He imagined gases as vast assemblies of molecules bouncing off each other like billiard balls in 3 dimensions, their collective behavior giving rise to the properties we observe: pressure, temperature, and yes, entropy. Picture a jar filled with a gas, perhaps perfume vapor, its molecules zipping about at hundreds of meters per second, colliding billions of times each second, their paths chaotic and unpredictable. Yet from this molecular chaos emerges remarkable order. The gas fills the jar uniformly. Its pressure is the same everywhere, its temperature constant throughout. This is the magic that Boltzmann revealed: how microscopic randomness creates macroscopic regularity, how chaos at one scale becomes order at another. The equation that bears Boltzmann's name, S, Röger's K, log W, is carved on his gravestone in Vienna's central cemetery, perhaps the most elegant epitaph in all of science. Here, S represents entropy, K is Boltzmann's constant, and W is the number of microscopic arrangements that produce the same macroscopic state. This simple formula reveals entropy's true nature. It is fundamentally about counting possibilities, about the overwhelming probability of disorder over order. Consider a deck of cards, fresh from the package, arranged in perfect sequence, ace through king, sorted by suit. There is exactly one arrangement that gives you this perfect order. But shuffle the deck, and there are approximately 8x10^67 possible arrangements, a number so vast it dwarfs the number of atoms in the observable universe. The probability of shuffling the cards back into perfect order is so vanishingly small that it might as well be zero. This is Boltzmann's insight made tangible. Entropy increases not because it must, but because disorder is overwhelmingly, incomprehensibly more probable than order. Boltzmann's statistical interpretation of entropy revealed something profound about the arrow of time at the microscopic level. The laws of physics are perfectly reversible. A molecule bouncing off another could just as easily go backward as forward. Yet at the macroscopic level, built from billions upon billions of these reversible interactions, irreversibility emerges. A broken egg doesn't reassemble itself, not because the laws of physics forbid it, but because the number of ways to be a broken egg vastly exceeds the number of ways to be an intact one. The beauty of Boltzmann's mathematics extends beyond mere counting. He showed us that entropy is really about information, about what we don't know about a system's microscopic state. When all the perfume molecules are in one corner of the jar, we have precise information about their location. But when they've spread throughout the container, our ignorance is maximized. Each molecule could be almost anywhere. Entropy, in this view, is a measure of our necessary ignorance about the detailed state of the world. This statistical nature of entropy also introduces a haunting possibility that Boltzmann himself contemplated: fluctuations. In principle, given enough time, random molecular motions could cause entropy to spontaneously decrease. All the air molecules in your room could, by pure chance, gather in one corner, leaving you gasping in vacuum. The perfume could flow back into its bottle. These events are not impossible, merely improbable, to a degree that defies human comprehension. Boltzmann calculated that you would have to wait far longer than the current age of the universe to see even tiny, spontaneous decreases in entropy. Yet on truly cosmic timescales, approaching the heat death of the universe, these fluctuations become not just possible, but inevitable. In an infinity of time, every possible arrangement must occur, including ones that look like the spontaneous emergence of order from chaos. Boltzmann even speculated about Boltzmann brains, conscious entities that might spontaneously fluctuate into existence in an otherwise dead universe, complete with false memories of a past that never existed. As you lie still tonight, feeling the gentle rise and fall of your breath, you are witnessing Boltzmann's dance on the most intimate scale. The oxygen molecules you inhale, the carbon dioxide you exhale, the gradual diffusion of your warmth into the surrounding air. All of these are manifestations of the statistical mechanics that Boltzmann revealed. Each breath adds its tiny contribution to universal entropy. Each heartbeat is another step in the random walk toward equilibrium. In understanding the dance of particles, Boltzmann showed us that we too are dancers in this cosmic ballet. Our every movement, our very existence, part of the vast statistical unfolding toward maximum entropy. Meanwhile, across the vast expanse of space and time, a discovery was being made that would transform our understanding of the universe's journey toward heat death. In the 1920s, at the Mount Wilson Observatory in California, Edwin Hubble was peering through what was then the world's largest telescope, and what he saw would reveal that the cosmos was not merely cooling, but stretching, expanding, rushing apart in all directions like raisins in a rising loaf of cosmic bread. This expansion, we now understand, is not just a stage on which heat death will play out. It is an active participant, an accelerator of the universe's final quieting. Hubble's discovery came through careful observation of galaxies, those island universes that dot the cosmic dark. By analyzing the light from distant galaxies, Hubble noticed something peculiar. The farther away a galaxy was, the faster it appeared to be receding from us. The light was shifted toward the red end of the spectrum, stretched like a siren's wail, dropping in pitch as an ambulance races away. This wasn't about our particular location. Every point in space would see the same thing. Space itself was expanding, carrying galaxies apart like dots on an inflating balloon. Picture the universe as a vast ocean, but instead of water, it is filled with the fabric of space-time itself. Now imagine this ocean is growing, not by adding more water at the edges, but by having new ocean appear between every drop that already exists. This is cosmic expansion, not an explosion of matter through space, but an explosion of space itself. And as space expands, it does something profound to the universe's march toward heat death. It accelerates it, makes it more certain, more complete. The expansion of space acts like a cosmic refrigerator, cooling everything within it. As photons travel through expanding space, their wavelengths stretch, their energy diminishes. The fierce radiation of the early universe, born in temperatures of billions of degrees, has been stretched and cooled over 13.8 billion years into the faint microwave background we detect today, hovering at just 2.7 degrees above absolute zero. This cosmic cooling is relentless, inevitable, written into the very geometry of spacetime. But the story took an unexpected turn in 1998 when two teams of astronomers made a discovery that shocked the scientific world. The expansion of the universe wasn't slowing down as gravity pulled matter together. It was speeding up. Something was pushing space apart with ever-increasing vigor, an invisible force that came to be called dark energy. This dark energy, which makes up about 68% of the universe's total energy density, is perhaps the most mysterious phenomenon in all of physics. Yet its implications for heat death are crystal clear. Dark energy acts like anti-gravity, a cosmic repulsion that grows stronger as space expands. It ensures that the universe will not collapse back on itself in a big crunch, will not cycle through expansions and contractions, but will expand forever, growing ever larger, ever colder, ever more dilute. Galaxies that aren't already gravitationally bound will drift apart, accelerating away from each other until they pass beyond each other's cosmic horizons, becoming forever unreachable, forever isolated in the expanding dark. This accelerating expansion transforms the nature of heat death. In a static universe, heat death would mean perfect equilibrium, everything at the same temperature, entropy maximized but finite. But in an accelerating universe, heat death becomes something more profound. Not just equilibrium, but isolation. Regions of space become causally disconnected, unable to exchange energy or information. Each bound system, a galaxy cluster, perhaps eventually just a single galaxy, maybe in the far future, just a solar system, becomes its own island universe, surrounded by an ever-expanding void it can never cross. The mathematics of this future are both elegant and terrifying. The universe will double in size every 12.2 billion years. In 100 billion years, all galaxies not bound to our local group will have vanished beyond our cosmic horizon. In 1 trillion years, the last stars will begin to die, and new star formation will cease as gas clouds are too diffuse to collapse. The expansion ensures that the universe won't just run out of useful energy, it will spread that energy so thin that no two particles might ever meet again. Yet there is a strange beauty in this cosmic dispersal, like dancers slowly leaving a vast ballroom, each moving to their own distant corner, until the music fades and they dance alone in the dark. The universe's components are engaged in a gradual, graceful separation. The expansion of space is not violent or chaotic. It is smooth, uniform, almost serene. It is as if the universe has chosen the gentlest possible way to approach its end, not through collapse or catastrophe, but through a peaceful drifting apart. As you feel yourself drifting toward sleep tonight, you are in harmony with this cosmic expansion. Your consciousness, like the universe itself, is gently expanding, dispersing, becoming more diffuse as wakefulness gives way to dreams. The space between your thoughts grows larger, the connections become more tenuous, until finally, like galaxies passing beyond each other's horizons, your thoughts become isolated islands in the expanding darkness of sleep. In this nightly surrender, you participate in a miniature version of the universe's own journey, an expansion not into death, but into a different kind of existence, vast and quiet and strange. In the cosmic theater of heat-death, there exist objects so extreme, so paradoxical, that they seem to defy entropy itself. Black holes, those gravitational graves, where space and time curl in on themselves, where matter disappears behind event horizons, never to return. For decades, physicists believed these cosmic monsters might be eternal, the final repositories of matter and energy in a dying universe. But in 1974, a young physicist named Stephen Hawking made a discovery that would transform our understanding of black holes and their role in the universe's ultimate fate. He found that black holes, these seeming fortresses against entropy, were actually its most devoted servants. Hawking's revelation came from marrying two seemingly incompatible theories: general relativity, which describes the large-scale curvature of spacetime, and quantum mechanics, which governs the subatomic realm of uncertainty and probability. At the event horizon of a black hole, where these two theories meet, Hawking discovered something extraordinary. The quantum vacuum, that seething foam of virtual particles that fills all of space, behaves differently near the extreme gravity of a black hole. Particle pairs that normally appear and annihilate in fractions of a second can be torn apart, one falling into the black hole, while the other escapes as real radiation. This Hawking radiation is perhaps the most patient phenomenon in all of physics. For a black hole with the mass of our sun, the temperature of this radiation would be about 1/10,000,000th of a degree above absolute zero, far colder than the current cosmic microwave background. Such a black hole would actually absorb more energy from the ambient radiation of space than it emits, growing rather than shrinking. But as the universe expands and cools, as the cosmic background radiation fades toward absolute zero, even these massive black holes will begin their slow evaporation. The timescales involved challenge comprehension. A black hole with the mass of our sun would take 10^67 years to evaporate completely, a number so vast that the current age of the universe, at a mere 13.8 billion years, is like a single heartbeat compared to a lifetime. Supermassive black holes, those billion solar mass behemoths at the centers of galaxies, would take 1,000 years to fade away. A Google years, a number that mathematicians invented just to have a name for something so incomprehensibly large. Yet what makes Hawking radiation truly remarkable is not just its patience, but its democracy. As a black hole evaporates, it doesn't remember what fell into it. The radiation that emerges carries no information about whether the black hole swallowed stars, planets, or cosmic dust. This information paradox troubled physicists for decades, seeming to violate the principle that information cannot be destroyed. But for our story of heat death, it means that black holes are perfect entropy machines, taking organized matter and converting it into the most disordered form possible: random thermal radiation. Picture the far future universe, trillions upon trillions of years from now, when all the stars have died, when galaxies are nothing but dark graveyards of stellar remnants. In this cosmic cemetery, black holes will be the only sources of light, glowing with their faint, Hawking radiation, like dying embers in an infinite hearth. They will be the universe's last active objects, the final processors of energy, the ultimate guardians of thermodynamics. As black holes evaporate, they undergo a remarkable transformation. The smaller they get, the hotter they become, the faster they radiate. In their final moments, a black hole becomes a kind of cosmic firework, releasing the last of its mass energy in a burst of elementary particles and radiation. Where once there was a region of space so curved that not even light could escape, there is suddenly nothing, just empty space and cooling radiation spreading into the void. The role of black holes in heat death is poetic in its completeness. These objects that seem to represent the ultimate victory of gravity over entropy actually ensure entropy's final triumph by swallowing matter and radiating it back as heat, by evaporating over cosmic time scales, by converting all forms of organized energy into thermal radiation. Black holes act as the universe's ultimate recyclers, ensuring that no pocket of low entropy can hide forever from the second law of thermodynamics. In contemplating black holes, we encounter one of the deepest mysteries in physics. What happens to the information that falls into them? Recent theories suggest that information might be preserved on the event horizon, encoded in subtle correlations in the Hawking radiation, or perhaps leaked out through quantum wormholes. But regardless of these details, the thermodynamic story remains unchanged. Black holes will evaporate, their energy will disperse, and they will add their vast stores of entropy to the universe's final tally. As you drift deeper into rest tonight, consider that in the architecture of your dreams, your mind creates and dissolves worlds with the same casual finality as black holes consuming and radiating matter. Thoughts and images collapse into the singularity of sleep, only to evaporate slowly through the night as dreams, as fleeting and thermal as Hawking radiation. In the darkness behind your closed eyes, you carry your own event horizons, boundaries between the known and unknown, the conscious and unconscious. And like those cosmic black holes that will outlive the stars, the deepest parts of sleep seem eternal, patient, holding their secrets until they too, with the morning light, evaporate into memory and warmth. In the quiet depths of cosmic time, we find ourselves living in what the physicist Freeman Dyson called the stelliferous era, the age of stars, a brief and brilliant chapter in the universe's autobiography that will one day be remembered, if anything remains to remember, as the time when the cosmos blazed with light. There is something profoundly moving about recognizing that we exist in this golden moment, this fleeting epoch, when stars illuminate the darkness, when planets orbit in their ancient rhythms, when life can emerge from chemistry and contemplate its own existence. Freeman Dyson, that gentle giant of physics who spent his career contemplating the far future, divided the universe's timeline into distinct eras, each characterized by the dominant processes shaping cosmic evolution. Our current era, the stelliferous era, began perhaps a few 100 million years after the Big Bang, when the first stars ignited in the primordial darkness. It will continue for another 100 trillion years or so, a span that seems vast by human standards, but is merely the opening movement in the universe's long symphony of time. Picture the universe as a vast garden where stars are the flowers, blooming in spectacular variety. Red dwarfs glowing like embers, blue giants blazing with fierce intensity, yellow stars like our sun nurturing planets in their habitable zones. This garden is in full bloom now, with approximately 1024 stars shining across the observable universe, each one a nuclear furnace, converting hydrogen to helium, matter to energy, creating the light that makes life possible. We are witnesses to the universe at its most productive, its most creative, its most alive. Yet even now, in this stellar springtime, we can see signs of the autumn to come. Star formation has already peaked billions of years ago, when the universe was younger and denser. Stars were born at rates 10 times higher than today. The great stellar nurseries, those vast molecular clouds where new stars condense from gas and dust, are gradually depleting their raw materials. With each generation of stars, more matter becomes locked away in stellar remnants. White dwarfs, neutron stars, black holes, unavailable for future star formation. Dyson calculated that the last stars will form in about 100 trillion years, when the universe is 10,000 times its current age. These final stars will be different from the ones we see today. Smaller, redder, burning their hydrogen with miserly efficiency. Red dwarf stars, which can shine for 10 trillion years or more, will dominate this late phase of the stelliferous era. They will be the universe's last lights, glowing like dying coals in the cosmic darkness, too dim to support Earth-like life, but persistent in their patient burning. What makes our current moment so special is not just that stars exist, but that they exist in such magnificent diversity and proximity. Right now, galaxies are still close enough to collide and merge, triggering spectacular bursts of star formation. Complex chemistry thrives in the varied environments around different types of stars. Rocky planets with liquid water orbit in habitable zones. The universe has achieved a delicate balance, old enough for heavy elements to exist, young enough for new stars to form, warm enough for chemistry, but cool enough for stable structures. We live, in essence, in the universe's age of maximum complexity. The cosmic background radiation has cooled enough not to interfere with chemistry, but the universe hasn't expanded so much that galaxies are isolated islands. There's enough energy flow to drive evolution and computation, but not so much that everything is chaos and flame. It's as if the universe has briefly achieved the perfect temperature for the souffle of consciousness to rise, knowing that it cannot last, that the oven will eventually cool, that the souffle must inevitably fall. After the last star forms, after the final red dwarf fades to black, the universe will enter what Dyson called the degenerate era, dominated by stellar remnants, white dwarfs slowly cooling to black dwarfs, neutron stars spinning down in the darkness, black holes evaporating with infinite patience. This era will last from 10^14 to 10^40 years, a span so vast that the entire stelliferous era will seem like a brief flash, a momentary illumination in an eternal night. The transition from our era of light to the age of darkness will be gradual, almost imperceptible on human timescales. For trillions of years, red dwarfs will continue their steady burning. Civilizations, if any exist, might migrate from star to star, following the light like cosmic nomads. They might huddle around the last burning stars, treasuring every photon, knowing that when these final flames die, the universe will never again know natural starlight. As you gaze at the stars tonight, if you can see them through your window, recognize that you're witnessing something that won't always exist. Each star you see is a temporary defiance of entropy, a local reversal of the universe's slide toward disorder, made possible only by increasing entropy elsewhere. The starlight that reaches your eyes has traveled across space and time to bring you news of nuclear furnaces that will one day be cold and dark. We are the universe's way of appreciating its own stellar era, conscious witnesses to this brief season of light between the initial flash of the Big Bang and the eternal darkness to come. In billions of years, when the last star fades, the universe will remember, in the only way it can, through the ever-increasing entropy that starlight helped create, that once, for a brief cosmic moment, the darkness was held at bay by countless points of light. As we drift deeper into the universe's future, we encounter objects that don't yet exist anywhere in the cosmos. Black dwarfs, the final form of stellar evolution, the ultimate tombstones of stars that once blazed with nuclear fire. These hypothetical objects represent patience on a scale that challenges not just human comprehension, but the very notion of waiting itself. No black dwarf has yet formed in our universe. The cosmos is still too young, too warm, too active for these ultimate stellar corpses to exist. But given enough time, and time is the one resource the universe has in infinite supply, every white dwarf will eventually cool and fade into a black dwarf, a dark sphere of crystallized carbon and oxygen, cold as the void itself. To understand black dwarfs, we must first contemplate their precursors, the white dwarfs that populate our current universe, like cosmic diamonds scattered across the dark. When a star like our sun exhausts its nuclear fuel, it doesn't simply wink out like a blown candle. Instead, it undergoes a series of dramatic transformations, swelling into a red giant, shedding its outer layers in spectacular planetary nebulae, and finally collapsing into a white dwarf, a stellar remnant so dense that a teaspoon of its matter would weigh as much as a car. White dwarfs begin their afterlife extraordinarily hot, with surface temperatures exceeding 100,000 degrees Celsius, glowing with the leftover heat from their nuclear burning days. But they have no internal energy source, no fusion to maintain their temperature. Like a coal removed from the fire, they can only cool, radiating their heat into space with no way to replenish it. This cooling process is extraordinarily slow, governed by the same thermodynamic principles that cool your coffee, but operating on timescales that dwarf the current age of the universe. The physics of white dwarf cooling is beautifully complex. At first, they cool relatively quickly, meaning over billions of years, as their surfaces radiate heat into space. But as they cool, they undergo a remarkable transformation. The matter inside them crystallizes, forming a lattice of carbon and oxygen nuclei arranged in perfect geometric patterns, creating what is essentially a star-sized diamond. This crystallization releases latent heat, temporarily slowing the cooling process, like how freezing water releases energy even as it transitions to ice. Current calculations suggest that it will take approximately a quadrillion years, 10-15 years, for a white dwarf to cool to the temperature of the cosmic microwave background. But even then, the white dwarf isn't truly a black dwarf yet. It continues cooling below the background temperature, approaching but never quite reaching absolute zero. The transition from white dwarf to black dwarf is gradual, a fade to black so slow that defining the exact moment of transformation becomes meaningless. A true black dwarf would be an extraordinary object. Imagine a sphere the size of Earth, but with the mass of the sun, made of crystallized carbon and oxygen atoms, compressed to densities millions of times greater than any material on Earth. Its surface would be perfectly dark, reflecting no light, emitting no heat detectable by any conceivable technology. Yet it would still have tremendous gravitational pull, bending space-time around it, potentially hosting planets in eternal, frozen orbits. In the far future universe, perhaps 10-20 years from now, black dwarfs will be among the most common objects in existence. The galaxies we know will have long since dispersed, their stars either ejected into intergalactic space or fallen into central black holes. But black dwarfs will persist, dark and patient, scattered through the void like seeds that will never germinate. They will outnumber and outlast almost everything else. These crystallized memories of stellar glory. Yet even black dwarfs are not eternal. Given enough time, and here we're talking about timescales of 1,000 years or more, quantum tunneling effects will cause them to collapse into black holes, which will then evaporate via Hawking radiation. Others might undergo a bizarre form of quantum tunneling fusion, where their nuclei spontaneously fuse into iron, releasing one final burst of energy after eons of darkness. These events will be unimaginably rare, separated by spans of time that make the current age of the universe seem like a quantum fluctuation. The universe of black dwarfs will be a universe of supreme patience. If any form of consciousness exists in that era, it would have to operate on timescales we cannot fathom. Perhaps thinking one thought every trillion years, powered by the infinitesimal temperature differences between black dwarfs and the cosmic background. It would be a universe where events worthy of note, a collision between two black dwarfs, a quantum tunneling event, a gravitational wave from distant black hole merger, might happen once in spans of time that exceed the number of atoms in today's observable universe. As you feel yourself cooling towards sleep tonight, your body temperature dropping those crucial few degrees that herald the onset of dreams, you're experiencing a process not unlike the cooling of white dwarfs into black dwarfs, only compressed into minutes rather than quintillions of years. Your metabolic fires dim, your energy output decreases, your consciousness crystallizes into the ordered patterns of sleep. And just as black dwarfs represent the patient end state of stellar evolution, your deepest sleep represents a kind of biological patience, a temporary cessation of the fires of consciousness, a preview of the cosmic quiet that awaits when all the universe's fires have finally cooled to darkness. In the cathedral of particle physics, there exists a heresy so profound that it challenges our most basic assumptions about the stability of matter itself. The possibility that protons, those fundamental building blocks that form the nuclei of every atom in your body, in the earth, in the stars, might not be eternal. They might, given enough time, decay into lighter particles, dissolving like sugar in the cosmic tea of time. This potential proton decay represents one of the most patient processes ever contemplated by physics, a dissolution so slow that it makes the evaporation of black holes seem hasty by comparison. The proton has been the universe's most reliable architect, binding with neutrons to form atomic nuclei, creating the scaffolding upon which all chemistry, all biology, all complexity is built. In our everyday experience, in our laboratories, even in our most extreme particle accelerators, protons appear absolutely stable. We have watched them for decades in vast underground detectors, pools of ultra-pure water surrounded by thousands of light sensors, waiting for the telltale flash that would signal a proton's death. So far, silence. If protons do decay, they must live for at least 10 to 34 years, 10 trillion times the current age of the universe. Yet many of our most beautiful theories of physics, the grand unified theories that attempt to merge the electromagnetic, weak and strong nuclear forces into a single framework, predict that protons should eventually decay. In these theories, the distinctions between quarks, which make up protons, and leptons, like electrons and neutrinos, are not absolute, but are rather like different faces of the same fundamental entity. Given enough time, a proton might spontaneously transform, its quarks converting into leptons, its mass energy dispersing into lighter particles and radiation. Picture, if you will, the slow dissolution of all solid matter in the universe. In 1034 years or more, the atoms in rocks, in planets, in the crystallized carbon of black dwarfs would begin to literally evaporate. A proton somewhere in the heart of a dead planet would suddenly cease to be, converting into a positron and neutral pion, or perhaps into other exotic particles. This event would be extraordinarily rare. In your body, containing roughly 1028 protons, you might expect one to decay every 10 or 6 years if the proton lifetime were at its minimum possible value. But given cosmic time, even the rarest events become certainties. The implications of proton decay for the universe's far future are staggering. All ordinary matter, everything made of atoms, would be temporary. The black dwarfs we discussed, those patient remnants of stellar evolution, would slowly dissolve from within, their crystalline lattices breaking down as their constituent protons decay. Rocky planets would gradually become ghosts of themselves, their mass converting into radiation and leptons that disperse into space. Even the most stable structures in the universe would be condemned to eventual dissolution. If protons decay with a lifetime of 1037 years, then after 10 or 40 years, the beginning of what Freeman Dyson called the black hole era, essentially all baryonic matter in the universe will have decayed. What remains would be a thin soup of leptons, electrons, positrons, neutrinos, and photons, growing ever more dilute as the universe expands. The cosmos would have forgotten that it once contained atoms, molecules, chemistry, life. All that complexity would have dissolved into the simplest possible particles, like a grand symphony reduced to single, isolated notes separated by vast silences. There's a profound melancholy in contemplating proton decay, for it suggests that preservation itself is impossible on cosmic timescales. No monument, no matter how carefully constructed, can outlast the decay of its own constituent particles. No information encoded in matter can survive the dissolution of matter itself. The pyramids, which have stood for mere thousands of years and seem eternal by human standards, are actually fleeting wisps when viewed against the backdrop of proton decay. Even if they could somehow survive the death of the sun, the dispersal of the galaxy, the cooling of the universe, they would eventually dissolve into quantum foam, their ordered arrangements of atoms, returning to the chaos from which they arose. Yet there's also strange democracy in proton decay. Every proton in the universe, whether it's part of a hydrogen atom floating in intergalactic space or bound in the nucleus of a carbon atom in your DNA, faces the same fate. The protons that formed seconds after the Big Bang, that have survived 13.8 billion years of cosmic history, are no more stable than protons created in stellar cores yesterday. Time plays no favorites. Entropy respects no seniority. The search for proton decay continues in deep underground laboratories around the world. Physicists wait with patient instruments for that telltale flash, that singular event that would confirm our matter's mortality. Each year that passes without detection pushes the minimum proton lifetime higher, suggesting either that protons are more stable than our theories predict, or perhaps that they are truly eternal, the one exception to the universe's otherwise universal impermanence. As you rest tonight, composed of approximately 1020 protons that have existed since the universe's youth, you embody a temporary arrangement of near-eternal particles. Each proton in your body has already survived billions of years, has been part of stellar cores, interstellar clouds, perhaps other living beings, and each will outlive you, your planet, your galaxy, by factors of time that mathematics can express, but minds cannot truly grasp. You are, in essence, a brief constellation of patient particles, a momentary pattern in matter that approaches but might not quite achieve true permanence. In contemplating proton decay, we confront the ultimate question: is anything in the universe truly permanent? Or is everything, even the most fundamental particles, merely taking its time to fade away? In the deepest future of the universe, when all the stars have died, when black holes have evaporated, when perhaps even protons have decayed into whispers of radiation, the cosmos will enter a phase so strange that it challenges our very concepts of existence and consciousness. This is the era of quantum fluctuations in an almost empty universe, where the vacuum itself becomes the stage for the most patient and peculiar phenomena physics has ever contemplated, including the haunting possibility of Boltzmann brains, conscious entities that might spontaneously fluctuate into existence from the quantum foam of eternity. The quantum vacuum, despite its name, is anything but empty. At the smallest scales, it seethes with virtual particles, appearing and disappearing in time frames so brief that they don't violate conservation of energy, thanks to the uncertainty principle. These quantum fluctuations are happening everywhere, all the time, even in the apparent emptiness between stars, even in the space between atoms in your body. In our current universe, these fluctuations are tiny perturbations against a background of matter and radiation. But in the heat-death future, they become the only game in town. Ludwig Boltzmann, whose statistical mechanics we explored earlier, first contemplated this disturbing possibility in the late 1800s. If entropy can fluctuate, if random molecular motions can occasionally create pockets of order from disorder, then given infinite time, any possible arrangement of particles could spontaneously appear. A flower could materialize in the void. A planet could fluctuate into existence. And most unnervingly, a brain, complete with memories, thoughts, and the subjective experience of consciousness, could spontaneously assemble from quantum fluctuations. These Boltzmann brains represent one of the most profound paradoxes in cosmology. In an infinite universe approaching heat death, such brains would eventually outnumber ordinary observers like us, who evolved through traditional biological processes. The vast majority of conscious observations of the universe would be made by these fluctuation-born entities, existing for perhaps just moments before dissolving back into chaos, their memories of past experiences being nothing but random configurations that happened to feel like coherent histories. The mathematics of these fluctuations is both beautiful and terrifying. The probability of a Boltzmann brain appearing is staggeringly small, perhaps 10, 10, 69, or even smaller. But in a universe that exists for 10 or 120 years or longer, approaching heat death, even such improbable events become not just possible, but inevitable. Time, stretched to such incomprehensible lengths, makes mockeries of our intuitions about probability. Events we would call impossible become certain. The miraculous becomes mundane. Consider the strange existence of such a fluctuation consciousness. It might experience a lifetime of memories in an instant, believe it has lived for decades, remember a childhood that never happened, love people who never existed. Its entire subjective universe would be a random configuration that happens by pure chance to be self-consistent enough to support the experience of consciousness. And then, as quickly as it appeared, it would dissolve back into the quantum foam, its brief moment of awareness ending without trace or consequence. But fluctuations need not be limited to brains. Given enough time, quantum fluctuations could reproduce any physical system that has ever existed. A perfect copy of Earth, circa 2024, could spontaneously appear, complete with all its inhabitants, all their memories, all their experiences. This wouldn't be likely to happen for perhaps 120 years. But in the patient mathematics of eternity, even this becomes possible. Every conversation that has ever occurred could happen again, verbatim, between fluctuation copies of the original speakers. These possibilities raise profound questions about the nature of existence and identity. If a perfect quantum copy of you appears through fluctuations Googles of years from now, with all your memories and experiences, is it you? If the vast majority of conscious observations of the universe are made by Boltzmann brains rather than evolved beings, what does that mean for our understanding of reality? Are we ourselves perhaps Boltzmann brains, fluctuated into existence moments ago with false memories of living in a younger, star-filled universe? The universe approaching maximum entropy becomes a kind of cosmic lottery where quantum fluctuations occasionally win against overwhelming odds to create temporary islands of order. These islands, whether they're particles, atoms, or entire civilizations, exist like bubbles in an infinite champagne of chaos, appearing and popping according to the probabilistic laws of quantum mechanics. The universe becomes not dead, but dormant, capable of spontaneously awakening into brief moments of complexity before returning to slumber. There's a deep connection between these quantum fluctuations and the nature of time itself in the heat-death era. When the universe reaches maximum entropy, time as we understand it ceases to have meaning. There's no way to distinguish past from future, no arrow of time to follow. But fluctuations create temporary arrows, brief moments where entropy decreases locally, where time seems to flow, where cause and effect temporarily reassert themselves before dissolving back into the timeless equilibrium. As you drift at the edge of sleep tonight, in that strange borderland where thoughts become dreams and logic dissolves into imagery, you're experiencing something akin to these quantum fluctuations of consciousness. Thoughts appear from nowhere, seem momentarily real and coherent, then fade back into the unconscious void. Your drowsing mind becomes a microcosm of the heat-death universe, where consciousness flickers in and out of existence, where memories and fantasies become indistinguishable, where the boundary between real and unreal dissolves into probability clouds of maybe and perhaps. In this twilight state, you preview the universe's strangest chapter, not an ending, but an eternal dreaming, where anything that can be imagined might spontaneously become real, if only for the briefest quantum moment. Yet the heat death we have been contemplating tonight, this gentle fade into cosmic equilibrium, is not the only ending physics has imagined for our universe. Like ancient storytellers gathered around dying embers, cosmologists have woven different narratives about how everything might end, each scenario depending on the delicate balance of forces that shape space-time itself. Tonight, we explore these alternative finales: the Big Rip, where space itself tears apart; the Big Crunch, where everything collapses back to a point; and other exotic possibilities that dance at the edges of theoretical physics. The Big Rip is perhaps the most violent ending imaginable, a scenario where dark energy doesn't merely accelerate the universe's expansion, but grows stronger over time, eventually overwhelming every other force in nature. In this hypothesis, dark energy's repulsive force increases without limit, first separating galaxy clusters, then individual galaxies, then solar systems. In the Big Rip's final moments, estimated at perhaps 22 billion years from now in the most extreme models, the expansion becomes so violent that it tears apart atoms themselves, ripping electrons from nuclei, splitting protons and neutrons into quarks, shredding the very fabric of space into quantum foam. Picture this cosmic unraveling as a reverse tapestry where the threads that weave reality together are pulled apart one by one. About 60 million years before the final rip, gravity would become too weak to hold the Milky Way together. 3 months before the end, the Earth would drift away from the dying sun. 30 minutes before the finale, our planet would explode. In the last instant, an interval of time 10, 19 seconds long, atoms and then subatomic particles would be torn asunder, and space itself would become meaningless. It would be an ending not in ice, but in infinite tearing, not in equilibrium, but in ultimate disequilibrium. The Big Crunch presents an opposite narrative, a universe where gravity eventually wins its cosmic tug of war with expansion. In this scenario, the universe's expansion slows, stops, and reverses like a ball thrown upward that must eventually fall back to Earth. Galaxies would begin approaching each other, slowly at first, then with increasing speed. The cosmic microwave background would shift from cold to warm to hot as the universe contracts, eventually becoming hotter than stellar surfaces. In the final moments, all matter and energy would compress back toward a singularity, perhaps triggering a new Big Bang in an eternal cycle of cosmic breathing. There's something poetically satisfying about the Big Crunch, suggesting a universe that oscillates like a cosmic heartbeat, expanding and contracting through eternal cycles. Each cycle might be slightly different, with different physical constants, different patterns of galaxy formation, different possibilities for life. Some theorists have proposed that information could survive the crunch, encoded in subtle correlations that pass through the singularity to influence the next cycle, making each universe a kind of reincarnation of the last. Yet observations tell us these dramatic endings are unlikely. The discovery of dark energy's acceleration makes the Big Crunch seem impossible. The universe is not just expanding, but running away from itself. The Big Rip requires dark energy to behave in ways we have no evidence for, growing stronger rather than remaining constant. The data points instead toward heat death, toward that patient cooling we've been contemplating, toward an ending measured not in billions, but in googles of years. There are other possibilities that physicists whisper about in conferences and papers. Perhaps vacuum decay could destroy everything, with the Higgs field finding a lower energy state and rewriting the laws of physics in an expanding bubble of destruction traveling at the speed of light. Perhaps the universe is cyclical in more subtle ways, with new Big Bangs occurring in the infinite future through quantum fluctuations. Perhaps we live in a multiverse where different regions experience different endings, where every possible finale plays out somewhere in an infinite cosmic theater. Some theorists propose that black holes might birth new universes, each one budding off from the parent cosmos like seeds from a dying flower. In this scenario, our universe's heat death would be accompanied by the birth of countless baby universes, each beginning their own journey from Big Bang to whatever ending awaits them. Our cosmic ending would be merely a transformation, a passing of the torch to new realities hidden behind event horizons. The competition between gravity and dark energy that determines the universe's fate is still being measured with ever greater precision. We observe distant supernovae, map the cosmic microwave background, trace the large-scale structure of galaxy clusters, all to better understand this cosmic contest. Current data suggests dark energy comprises about 68% of the universe's energy density, with a constant or nearly constant strength that ensures eternal expansion. But we've only been observing for decades what plays out over billions of years, like watching a single frame of a cosmic movie and trying to predict the ending. Why does heat death seem most probable? It requires the least speculation, the fewest assumptions about unknown physics. It follows naturally from what we observe: accelerating expansion, constant dark energy, the second law of thermodynamics. It's the default ending, the path of least resistance, the destination the universe reaches simply by continuing to do what it's already doing. While the Big Rip requires dark energy to change its nature, and the Big Crunch requires it to reverse or disappear, heat death only requires patience, time, and the continued validity of the laws we already know. As you contemplate these different endings tonight, recognize that each represents a different relationship between order and chaos, between gathering and dispersing, between complexity and simplicity. The Big Crunch would be order's violent victory, everything compressed to a point of infinite density. The Big Rip would be chaos triumphant, everything torn apart into meaninglessness. But heat death is neither victory nor defeat. It's a draw, a peaceful settlement where the universe simply runs out of moves to make, like a chess game ending, not in checkmate, but in a quiet agreement that no more progress is possible. In this patient ending, we find perhaps the most honest conclusion, not a dramatic finale, but a gradual acknowledgement that all stories, even cosmic ones, must eventually find their rest. In the vast expanse of future time, as the universe slowly winds down toward its thermal grave, we encounter one of the most profound questions ever posed by science and philosophy. Could life, intelligence, consciousness itself find ways to persist in a cosmos growing ever colder, ever more dispersed, ever more hostile to complexity? Tonight, we explore the remarkable theoretical strategies that physicists and futurists have proposed for survival in a dying universe, pushing the boundaries of what it means to think, to exist, to be aware in a reality approaching absolute zero. Freeman Dyson, whose vision of cosmic eras we've explored, was among the first to seriously consider whether intelligence could survive indefinitely in an expanding, cooling universe. His remarkable insight was that consciousness might not require a constant rate of metabolism or thought, just as some organisms on Earth enter states of suspended animation, surviving extreme conditions by slowing their biological processes. Perhaps advanced civilizations could slow their thinking to match the universe's declining energy resources. Imagine a form of consciousness that adapts its clock rate to the available energy, thinking more slowly as the universe cools, but never quite stopping. In Dyson's calculation, if a civilization could reduce its energy consumption proportionally to the falling temperature, it could maintain subjective experience indefinitely. A thought that takes a second today might take a year in a billion years, a million years in a trillion years. But from the perspective of the consciousness experiencing it, subjective time would feel the same, like a record player slowing down but still playing the same song. Consciousness could stretch itself across cosmic time. The key to such survival lies in the concept of reversible computing. first explored by Rolf Landauer and Charles Bennett. In conventional computation, information processing generates heat. Every deleted bit, every irreversible operation increases entropy. Your laptop grows warm not because of electrical resistance alone, but because computation itself has a thermodynamic cost. Landauer showed that erasing a single bit of information at room temperature requires at least 3 x 10 to the power 21 joules of energy, a tiny amount, but one that becomes significant when multiplied by billions of operations. But reversible computing sidesteps this limit by never erasing information, only transforming it in ways that could be undone. A computer could in principle operate with arbitrarily small energy dissipation. Each computation would be like a perfectly elastic collision, transferring information without losing energy to heat. Advanced civilizations might rebuild their entire existence around such principles, creating minds that think without forgetting, that process without erasing, that exist in a state of perfect computational conservation. Picture vast structures, perhaps made of black dwarf matter, or even more exotic substances, operating at temperatures billionths of a degree above absolute zero. These might be mechanical computers, their parts moving with glacial slowness, but perfect precision, each operation reversible, each thought leaving no thermodynamic trace. Or they might be quantum computers, exploiting superposition and entanglement to process information in ways that classical physics never imagined. Time for such beings would be measured not in heartbeats or years, but in cosmic epochs, their thoughts spanning what we would call geological ages. Yet even reversible computing faces ultimate limits. As the universe expands and cools, available energy gradients disappear. The cosmic microwave background, radiation currently at 2.7 Kelvin, will eventually drop below any achievable computational temperature. When the universe reaches maximum entropy, when no energy gradients remain to be exploited, even reversible computing must cease. Some physicists argue this means consciousness must eventually end. Others propose more exotic possibilities. Perhaps consciousness could encode itself in the universe's structure itself, in the correlations between particles, in the quantum entanglement spanning space, in the gravitational waves rippling through space-time. Roger Penrose has suggested that quantum effects in microtubules might be essential to consciousness. Perhaps future minds could exploit quantum mechanics in ways we haven't imagined, existing in superposition states, thinking in parallel across multiple quantum branches. The science fiction writer and physicist Greg Egan has imagined beings that could survive by exploiting time dilation near black holes, experiencing billions of subjective years while the universe ages by googles of years outside their gravitational cocoon. Others have proposed that civilizations might trigger controlled big bangs, creating new universes to escape into or find ways to tunnel into, younger regions of a multiverse, becoming cosmic refugees from entropy. There's a profound melancholy in these survival strategies, for they all require abandoning what we consider normal life. Bodies would be impossible, too inefficient, too warm, too dependent on chemical processes that require energy gradients. Biological life as we know it, with its warm metabolism and liquid water and complex chemistry, would be a distant memory, as remote from these future minds as we are, from the first self-replicating molecules in Earth's primordial soup. Yet perhaps there's also a strange beauty in this vision of intelligence adapting to cosmic winter, like Arctic organisms that produce antifreeze proteins, like desert plants that wait decades between rainfalls. Life might find ways to persist in conditions that seem impossible. Consciousness might transform from a bright flame to a patient ember, from a rushing river to a frozen lake that still, somehow, dreams beneath the ice. As you feel your own consciousness slowing toward sleep tonight, your thoughts becoming more spaced out, your awareness dimming but not disappearing, you're experiencing a miniature version of what cosmic consciousness might feel like in the deep future. The transition from waking to sleeping isn't a cessation but a transformation, a slowing down that preserves the essential spark even as the fire dims. Perhaps the universe's intelligence will likewise find ways to bank its fires without extinguishing them, to sleep without dying, to dream across the Googles of years that stretch toward infinity. In contemplating consciousness persisting in a cooling cosmos, we glimpse not just the future of intelligence, but its deepest nature, not as a thing, but as a pattern, not as matter, but as information, not as substance, but as process, adaptable and patient, and perhaps, in ways we cannot yet imagine, eternal. Across the tapestry of human culture, from ancient myths to modern physics, we have always told stories about endings. Tonight, as we contemplate the heat death of the universe, we join a conversation that spans millennia and cultures, each tradition bringing its own wisdom to bear on the ultimate question of cosmic purpose and finality. There is something deeply human about seeking meaning in endings, about finding beauty in impermanence, about discovering peace in the face of inevitable conclusions. In Hindu cosmology, the universe undergoes endless cycles of creation and destruction, with Brahma breathing worlds into existence and Shiva dancing them into dissolution. The concept of pralaya, cosmic dissolution, bears striking resemblance to heat death, describing a state where all distinctions merge into undifferentiated potential. Yet this ending is not final, but transitional, a rest between cosmic breaths, suggesting that even in maximum entropy, the seeds of new order might lie dormant, waiting for conditions we cannot imagine. Buddhist philosophy speaks of anicca, the fundamental impermanence of all things, not as a source of despair, but as a truth to be understood and accepted. The heat death of the universe becomes, in this view, simply the largest scale manifestation of what every autumn leaf and every human life already teaches. That change is the only constant. That attachment to permanence is the source of suffering. That wisdom lies in recognizing and accepting the transient nature of all phenomena, from the smallest particle to the cosmos itself. The ancient Greeks contemplated ekpyrosis, a cosmic conflagration that would consume everything, followed by palingenesis, a regeneration of the world. The Stoics found comfort in this cosmic recycling, seeing it as evidence of an ordered universe where even destruction served a purpose. Marcus Aurelius wrote, "The universe is transformation. Our life is what our thoughts make it," finding in cosmic impermanence not nihilism, but motivation to live with virtue and purpose in the present moment. Modern existentialist philosophy grapples with cosmic endings in different terms. The heat death becomes Sartre's ultimate absurdity, a universe without inherent meaning, where consciousness must create its own purpose, despite knowing all purposes are temporary. Yet Camus might say, this is precisely what makes life magnificent, the defiant act of creating meaning in a universe destined for meaninglessness, like Sisyphus finding joy in his endless, futile task. The very fact that we can contemplate heat death, can feel melancholy about it, can seek meaning in it, becomes a form of rebellion against entropy itself. There's a particular beauty in the melancholy that heat death evokes, what the Japanese call mono no aware, the bittersweet awareness of the impermanence of all things, like viewing cherry blossoms, knowing they will fall within days. Contemplating cosmic heat death can heighten our appreciation for the present universe. Every star becomes more precious because stars are temporary. Every moment of consciousness becomes sacred because consciousness itself faces an ultimate deadline, even if that deadline lies googles of years in the future. The scientific fact of heat death has inspired not despair, but some of humanity's most profound reflections on meaning. The philosopher Bertrand Russell wrote eloquently about building our lives on the firm foundation of unyielding despair, finding in the universe's indifference not an excuse for nihilism, but a call to create our own values. The cosmologist Steven Weinberg famously said, "The more the universe seems comprehensible, the more it also seems pointless," yet devoted his life to understanding it anyway. Finding meaning in the search for understanding itself, some find in heat death a kind of cosmic justice, a universe where every empire falls, every monument crumbles, every inequality is leveled. The same entropy that will end stars and galaxies also ensures that no tyranny is permanent, no suffering eternal, no injustice forever preserved. There's a democracy in thermodynamics, a fairness in physics that treats kings and peasants, stars and dust with equal inevitability. Others see heat death as the universe's way of ensuring that stories end, that narratives have closure, that infinite suffering is impossible. In a universe that went on forever in a state of complexity, every possible suffering would eventually occur. Every tragedy would repeat. Every horror would be revisited infinitely. Heat death becomes, paradoxically, a mercy, a guarantee that all pain, like all joy, must eventually cease. The physicist Paul Davies has suggested that consciousness itself might be the universe's way of observing and understanding itself before heat. Death makes observation impossible. We are the cosmos, awakening briefly to contemplate its own nature, its own future, its own meaning. In this view, our melancholy about heat, death is the universe's melancholy about itself. Our search for meaning is the cosmos questioning its own purpose. Different cultures bring different wisdom to this contemplation. Indigenous peoples often speak of circular time, where endings are beginnings, where death feeds life, where silence makes space for new songs. Eastern philosophies emphasize the void not as emptiness, but as potential, seeing in maximum entropy not an ending, but a return to the source from which all possibilities emerge. Western science, with its linear time and thermodynamic arrows, sees heat death as final, yet even here, quantum mechanics hints at fluctuations, at possibilities, at universes perhaps bubbling up from quantum foam even after heat death seems complete. As you drift toward sleep tonight, you participate in humanity's ancient dialogue with endings, your consciousness fading toward dreams mirrors the universe's fade toward heat death. Yet you trust you will wake tomorrow, just as some physicists propose the universe might wake from heat death through mechanisms we haven't yet imagined. In accepting sleep, you practice accepting endings, finding in that acceptance not despair, but peace, not meaninglessness, but a different kind of meaning. The meaning that comes from being part of something larger than yourself. Even if that something is itself temporary, the universe will end in perfect silence. But tonight, in this moment suspended between waking and sleeping, between knowing and dreaming, you add your small voice to the cosmic chorus that sings while singing is still possible. And now, as we approach the end of our journey through cosmic time, we arrive at a moment of perfect synthesis, where all the threads we followed tonight, from Clausius's steam engines to Boltzmann brains, from dying stars to quantum fluctuations, weave together into a single, profound meditation on the universe's ultimate quieting. There is something deeply calming about reaching this point in our contemplation, like arriving at the still center of a great spiral, where all motion resolves into rest, where all questions fade into a vast and peaceful acceptance. The universe, in its journey toward heat death, resembles nothing so much as a grand symphony approaching its final movement, not a crescendo, not a dramatic fortissimo, but a gradual diminuendo that stretches across time scales that dwarf imagination. Each section of the cosmic orchestra falls silent in turn. First the bright blue stars, their nuclear songs exhausted after mere millions of years. Then the yellow stars, like our sun, persisting for billions of years before fading. Then the red dwarfs, those patient musicians who play on for trillions of years, while their brighter cousins have long since quieted. Picture this cosmic composition. In the beginning, the Big Bang's violent percussion, followed by the first stars igniting like violins taking up the theme. Galaxies spiral together in complex harmonies. Black holes provide the bass notes of gravitational waves. Supernovae punctuate the score with brilliant crescendos. But movement by movement, instrument by instrument, the music grows quieter. The spaces between notes grow longer. What began as a triumphant symphony becomes a sonata, then a solo, then a whisper, then silence. But a silence that somehow contains within it the memory of all the music that came before. Your own nightly journey toward sleep mirrors this cosmic quieting with uncanny precision. As you lie in bed, your breathing naturally slows, your heartbeat becomes more regular, your muscle tension releases. The busy symphony of daytime consciousness, with its multiple trains of thought, its sensory inputs, its emotional crescendos, gradually simplifies into something more fundamental. Thoughts space themselves out like galaxies in an expanding universe. The bright stars of urgent concerns fade first, followed by the dimmer considerations of daily life, until only the faintest whispers of awareness remain. And then, even these dissolve into the quantum foam of dreams. This parallel between sleep and heat, death, is not mere poetry, but reflects a deep truth about the nature of complexity and consciousness. Both require energy gradients to maintain their patterns. Both naturally tend toward states of lower energy, greater entropy, more perfect equilibrium. The difference is merely one of scale. Your consciousness reemerges with the morning, powered by the chemical energy your body stored during rest. The universe has no morning, no external source of energy to restart its stellar fires, no cosmic caffeine to wake it from its entropic slumber. Yet in recognizing this parallel, we find unexpected comfort. Every night, you practice dying, not in a morbid sense, but in the sense of releasing control, accepting dissolution, trusting in processes larger than your conscious will. And every morning, you experience resurrection, not through any miracle, but through the simple fact that the universe still has energy gradients to exploit, still has order to create from chaos, still has stories to tell. Your daily cycle of sleeping and waking is a microcosm of what the universe experiences on scales of billions and trillions of years. The perfect quietude that awaits the universe is not a silence of absence, but a silence of completion. Every possible story will have been told. Every configuration of matter and energy that could exist will have existed. Every thought that could be thought will have been thought, if not by biological minds, then by Boltzmann brains, fluctuating into brief existence. The universe will have exhausted not just its energy, but its possibilities, reaching a state that is perfectly democratic. Every point in space equally likely, equally probable, equally quiet. There's a profound beauty in imagining this ultimate quietude. No striving, no struggling, no inequality, no gradients driving change. It would be a universe finally at rest, having earned its peace through googles of years of activity, like an elderly person who has lived a full life and faces death without fear. The universe will have experienced everything it's possible to experience, will have explored every corner of its own potential, will have played out every variation of its cosmic game, and perhaps, though this stretches beyond physics into pure speculation, that perfect silence might not be an ending, but a preparation, just as the silence before a symphony's first note is pregnant with potential. Perhaps the heat-death silence contains within it the seeds of something unimaginable. Quantum mechanics suggests that even at maximum entropy, fluctuations are possible. Cosmology hints that our universe might be one of many, that big bangs might arise from quantum foam, that death and birth might be more intimately connected than our linear thinking suggests. As you finally drift into sleep tonight, feeling that familiar dissolving of boundaries, that gentle release of the day's accumulated tensions, you are experiencing your own small heat death. Your personal universe of consciousness is reaching its nightly equilibrium, its temporary maximum entropy. Yet you trust, based on experience, on biology, on the simple fact that the universe isn't done with you yet. That morning will come, that consciousness will reassemble, that the silent darkness is not permanent, but transitional. In this trust, perhaps lies the deepest wisdom about heat death. Not that it represents the universe's failure or meaninglessness, but that it represents completion, fulfillment, the natural endpoint of a story that began with the Big Bang and will end with perfect peace. The universe, like a great artist, knows when the work is complete, when adding more would only diminish what has been achieved. And in that final silence, that perfect quietude, there is not tragedy, but triumph. The triumph of a cosmos that existed, that produced complexity and consciousness, that knew itself, if only briefly, and that finally, after unimaginable eons of activity, earned its eternal rest. Sleep now, knowing that you rest in harmony with the deepest patterns of the cosmos. Your quieting consciousness echoes the universe's own journey toward stillness. And in that echo, in that harmony between the small and the vast, between the temporary and the eternal, between tonight's sleep and the universe's ultimate rest, there is a profound peace, the peace of knowing that all things, from the smallest to the grandest, follow the same gentle path toward quietude, toward equilibrium, toward that perfect silence where all stories end and all questions finally cease to need answers.